Uh, awesome. So, Matthias, thanks for joining us. I'm excited about this. You currently have an audience of pretty much exclusively people who do some degree of FM. Although that may change as more people hop on the call. We've got some hackers to come to our events as well. So, although they tend to appreciate SAT solvers in their own capacity. So I think it's a nice audience for this talk, and I'm excited to learn more about it. And thanks for joining us. So I'll let you take it away.
Okay, thanks. Thanks a lot for having me. Thanks for giving me the opportunity to talk about Bitwuzla. So, as the title says, well, I'm going to talk about our new SMT solver, Bitwuzla, which is a new SMT solver for bit-precise reasoning. What I mean with that, you will hopefully find out by the end of the talk what I mean with that. So, Bitwuzla is a new SMT solver for quantified and quantifier theories of fixed-size bit vectors, floating point arithmetic, arrays, and uninterpreted functions. And of course, all the possible combinations of these. And on the bottom of the slide, you see the pronunciation of Bitwuzla, and it's a bit hard to pronounce for English-speaking people, but the name actually is derived from an Austrian dialect expression, which is loosely translated, which can be loosely translated to for someone who tinkers with bits. So Bitwuzla is someone who tinkers with bits. So so I'm working on SMT solvers since over a decade now. So I started my PhD working on SMT solvers, and back then when I started my PhD, I started working on an SMT solver called Boolector. So maybe you already have heard of this one. And Boolector is an award-winning SMT solver, and it's a specialized solver for bit vectors and arrays. But the problem was back then, well, it's a huge monolithic C code base with a very rigid architecture, since Boolector itself only supported bit vectors with arrays, so that there was no modularity and so on. So overall, it was really cumbersome to maintain the code base and adding new features. So even adding new theories was really, really cumbersome. So that's where Bitwuzla comes into play. And the thing is, with SMT solvers, you really have to work quite some time on one developing a solver to actually know the in and outs and to actually be confident enough to start a new solver. So that's what we actually did. So initially, we started as Bitwuzla as an improved and extended fork of Boolector in 2018, but we never did an official release. And of course, since we just forked the code base, the limitations of the old Boolector code base still remained, right? What we still did is we added support for a floating point arithmetic and other features like answered cores and stuff like that. And in 2022, well, we decided we completely scratch the code base and start to rewrite the solver from scratch. And what we did there is now we've rewritten Bitwuzla in C++. And what we did there is we evaluated techniques that were implemented in Boolector, and we re-implemented or implemented techniques that were inspired by the techniques implemented in Boolector. So overall, we consider Bitwuzla the superior successor of Boolector. And Boolector will be very, very soon retired. I know if someone else already saw a talk by me, I was saying this quite. I was already saying this last year, but we're pretty close now to retiring Boolector, so that users can actually make the switch to Bitwuzla. So here are some selected features of the new solver. And in general, I have to say that the theories that we are supporting, the focus of is primarily theories that are used in hardware verification, but also software verification. So as I mentioned, it's arrays, bit vectors, floating point arithmetic, and uninterpreted functions, which are the most common theories for these kind of problems we are targeting. And of course, what we also support is quantified reasoning, and quantifiers can be combined with any of the supported theories. So that was something that the old versions were not able to do. And some other user-facing select features. So, by the way, if you have any questions, just interrupt me and yeah. So for user-facing features, what we have full incremental support. So we have incremental solving. We have a seamless interaction between multiple solver instances. So if a user wants to use different solver instances for different tasks, you can easily share formulas between the solver instances and things like that. Of course, when the solver returns satisfiable, we have models. Same for if it says the formula is unsatisfiable, it can return an answered core and answered assumptions. And Bitwuzla comes with a comprehensive and easy to use comprehensive and easy to use APIs. So the main API of Bitwuzla is C++, but then we also have a C API, a Python API. Currently OCaml bindings that we already have, and we already have planned to add Rust bindings. And yeah, it also supports the most common input formats for SMT solvers, so it's SMT version 2. Then there is another format, which is Boolector 2, which is more a model checking format. And then we'll also add support for SMT version 3 once it's finalized. So this is currently a work in progress, the new version. So this is a very well, it's an overview of all the components of Bitwuzla. So you can see here we have like this API layer on top of a few classes like solving context and node manager and things like that. The parser is built on top of the C++ API, and of course the command line interface is built on top of the parser. C API and Python API are also built on top of the C++ API. So I will get into this in the next slides. So I already mentioned that Bitwuzla is implemented in C++, so its main API is of course C++ API. We all have the other APIs on top of the C++ APIs, usually very thin wrappers. So the C API is a very thin wrapper on top of the C++ API, and same with the Python API. So let's go to the first a very central component of Bitwuzla, and that's the node manager, which is used for storing formulas and terms and types that users can create. So formulas are represented as reference-counted immutable nodes in a directed acyclic graph. And the node manager is responsible for managing and constructing these nodes and also types. And it employs hash counting to maximize sharing of subgraphs. And what we have here is the node manager is used to actually initialize a solving context. And a solving context is basically a solver instance, right? So you can give a solving context a bunch of formulas, and then it will solve these for you. So since you use the node manager to initialize the solving context, what enables the users there is to allow sharing between arbitrarily many solving contexts that were initialized with the same node manager. So that's something that was also not possible with the older version of Bitwuzla or with Boolector. Their nodes and formulas were really tied to a specific solver instance. So I already talked a little bit about the solving context, and the solving context is basically the internal equivalent of solver instance. And it, as I said, it determines the satisfiability of a set of asserted formulas, and it's fully configurable via options. It also provides an incremental interface for adding and removing assertions or formulas via push and pop interface. And yeah, it provides models for satisfiable queries and answers, of course, for unsatisfiable queries. And here in this diagram, you can see that the solving context consists of three main components. One is the rewriter, then the preprocessor, and the solver engine itself.
Matthias, does it do any kind of minimization for the models?
You mean, for example, removing redundant bits and things like that? No, actually not yet. So that's something users request, and that's something on our to-do list, but we don't do that yet.
Okay. Yeah,
that's a good point.
A lot of use cases, that sort of thing matters for explainability, right? Because
yeah. So the rewriter component is transforms terms via a predefined set of rewrite rules into semantically equivalent normal forms. So the rewriting is local, which means that it is independent from the current set of assertions in the solver solving context. So current rewrite of Bitwuzla implements about 230 rules, or I think now it's already more. And we distinguish between two types of rewrite rules. So we have required rewrite rules, and then we have optional ones. And these are grouped into three rewrite levels, 0 to 2. And level 0 rewrites are required rules. And these rules make sure that we eliminate, for example, certain operators, because inside of the solver, we have only a core set of bit vector operators, for example, that we want to deal with. But the bit vector theory supports a lot more operators. So what we are doing is, with these elimination rules, basically, is we rewrite these richer operators into the core set that is handled internally. So you can see, for example, here there is what we do. For example, we have a negation. So if you negate a bit vector, we translate this to bitwise negation and addition. So we don't have negation and subtraction inside of the solver, because you can express it with bitwise negation and addition. Then we have the level 1 rewrites, and these rewrites actually rewrite the node based on its immediate children only. So, for example, if we have an addition x plus 0, then we only look at its children, x and 0, and we can rewrite the term to x. So for the level 2 rewrites, we actually look at multiple levels of children. And this is, we separate them out in a different level, because this can be potentially harmful to the sharing of subgraphs in the formula. So because you can destroy sharing. So for example, here, what happens here is you have an equality over a minus b is equal to c, right? And you could rewrite this to b plus c is equal to a. So to get rid of the subtraction. But the problem is, if, for example, a minus b is occurring somewhere else in the formula, you would now introduce a new term, b plus c, right? So you have to be careful about these kind of things. So that's why they are separated out in an additional rewrite level. And all these rewrites are actually implemented as a pre-processing pass in the preprocessor. And preprocessor is invoked prior to solving. So the user gives the solving context a bunch of assertions, and then once the solver issues checksum, or wants to solve these assertions, the preprocessor tries to simplify these assertions. And what the preprocessor does is it applies global simplifications based on the current set of assertions. So it applies a bunch of preprocessing passes in a predefined order until fixed point. And currently, I think in Bitwuzla, let's see, we implement around 15 preprocessing passes, I think. And all these passes implement some set of satisfiability preserving transformations. And what's also new and was not in the old solver is that the preprocessor is fully incremental. So it also works with incremental solving and so on. And most of these passes are actually optional. So users can enable, disable them. We try to tune the default options of Bitwuzla so that it is usually the best configuration for most of the problems, user problems. But sometimes you might run into a weird edge case. Or for example, some pass does something weird with your formula, and you can just disable it. So there are a bunch of rewrites, bunch of preprocessing passes listed down below. So rewriting is, for example, one preprocessing pass, and here this one is actually the level 1. The level 0 rewrites are always applied. So these are not, you can't disable them because we have to rely on the fact that we only see this core set of operators in the internals of the solver. There are a bunch of other preprocessing passes like term substitution, where you have like top-level equalities of a constant and some term, where you can basically substitute that constant with the term in the whole formula and things like that. So there is a bunch of preprocessing passes that we do. The probably most important part is, of course, the solver engine, and the solver engine maintains the theory solvers for each supported theory. So it has a quantifiers module that reasons about quantified formulas, and it is also implemented as a theory solver. And the solver engine itself distributes relevant terms to theory solvers. So if you, for example, have an equality over bit vector terms, this is distributed to the bit vector solver. If you have a floating point predicate, then this is distributed to the floating point solver. And you can see here in this small diagram is that we have, well, I will come back to that later. So the solver engine also processes lemmas generated by the theory solver. So there is a back and forth communication between solver engine and the theory solvers. And the solver engine itself implements a lazy SMT paradigm lemmas on demand. So other solvers, for example, C3 and CDC5 are CDCLT solvers. Bitwuzla doesn't implement CDCLT, but it implements lemmas on demand. And what's different from the original lemmas on demand approach is that we actually use a bit vector abstraction of the formula, and instead of a propositional one. So the original lemmas on demand architecture had a Boolean abstraction of the formula, which meant that as soon as you have like theory predicates, right, these were abstracted as a Boolean variable, then you had a Boolean skeleton of the formula, and then you did lemmas on demand based on that Boolean skeleton. What we have in Bitwuzla is actually we have a bit vector abstraction, which means that everything bit vector related. So if we, for example, have bit vector equalities, inequalities, this is all part of the abstraction. And this also means that at the core of our solving engine, solver engine is actually a bit vector solver instead of a subsolver. So as you can see here, the PV solver is the core solver, and then there is this communication layer between the PV solver and these other theory solvers. So I talked about bit vector abstraction. So what is a bit vector abstraction? So the PV solver is actually responsible for reasoning about the Boolean and the bit vector terms of the formula. And in the bit vector abstraction, all non-bit vector theory atoms are abstracted as Boolean constants. So for example, if you have a floating point predicate, this is abstracted as a Boolean constant. If you have bit vector terms with non-PV operators, So for example, if you have a function application that is of type bit vector, then this gets abstracted as a bit vector constant. And once you do this abstraction, you end up with a bit vector formula that the PV solver can actually solve. And when you do this lemmas on demand, it's basically a counterexample guided refinement loop where the bit vector solver solves the bit vector abstraction if it's satisfiable. All the other theory solvers have to make sure that all the theory axioms are consistent with the current bit vector model. And once all the theories agree that the bit vector model of the bit vector abstraction is consistent with the theory axioms, we can return satisfiable. Or if the PV solver determines that the bit vector abstraction is unsatisfiable, then we can terminate with unsat. So I already talked a little bit about theory solvers. So here is more the techniques that the theory solvers implement. So the bit vector theory solver, its main approach is called bit blasting, which is a reduction of bit vectors to propositional logic. And how this happens is basically we take the bit vector terms, we construct bit representation circuits as n-inverter graphs. We use n-inverter graphs to represent these circuits. And then we translate these AIT circuits to CNF and then pass it on to a SAT solver. And this intermediate step going via AIGs also enables us to do more rewriting on the bit level. Then we have another orthogonal approach that's called ternary propagation-based local search, which doesn't use a SAT solver for solving the bit vector problem, but it's a local search algorithm that tries to find satisfying instances, satisfying assignments for a bit vector formula. So for the floating point arithmetic solver, we use an approach called word blasting, which is basically we translate floating point terms to bit vector terms. And then again, these bit vector terms get reduced to SAT. For arrays, we implement lemmas on demand for extension of the arrays that was also implemented in Boolector. But what we also support in contrast to Boolector is we support extensionality, also equality over nested arrays, and also constant arrays. And for interpreter functions, we implement dynamic accumulation, which basically adds lazy instantiations of function congruence axioms to the bit vector abstraction. And for quantifiers, we implement mod-based quantifier instantiation. So this is also, for example, implemented in C3. So I already talked a little bit about the APIs. So for the C++ APIs, C++ API, you can use this once you have the sources of Bitwuzla by including this header up here. It's in the CPP subdirectory. And the main classes of the C++ API are the term manager, then term and sorts, options, and the solver instance itself, Bitwuzla. And it also supports a parse interface to actually parse SMT2 and Bter2. And what users can do, for example, is they start parsing an SMT2 file and then they continue working on that instance with adding new assertions via the API and things like that. For the C API, we have a very thin, C API is a thin wrapper around the C++ API, but it is feature complete with the C++ API. And what we additionally have in C, since we don't have any automatic reference counting that we get in C++, we have optional, it's optional, but there is a manual reference counting for terms and sorts. So users can release resources as they as they want. So if they, for example, don't need specific objects anymore, they can manually decrease reference counts and stuff like that, so to free memory earlier. For Python, Python API is built on top of the C++ API via Cython, and it's also feature complete with the C++ API and has pretty much the same main classes as the C++ API. So on the bottom, I put 2 links there for the documentation of the APIs, and also we have a bunch of examples for each API, how this would look like in the different kinds of APIs we have. So it's also relatively easy to install. So the only things that you require for building actually Bitwuzla is a reasonably up-to-date version of Python. I think it's 3.7 right now. Then Mason, Ninja, and GNU GMP. And that's basically if you want to install Bitwuzla on your system, it's just these 4 commands you need to do to actually install it. Or if you just want to install the Python bindings, you can also just clone the repository and say pip install dot. Later on, we will also have Python PyPy packages, so that users don't even have to compile Bitwuzla on their own. But for now, that's pretty much the easiest steps you can do to install Bitwuzla. It also doesn't take too long to actually compile the solver. So this is so we also did an evaluation, of course, when we presented the new version of Bitwuzla, and we compared against different solver versions against Boolector, the most recent version of Boolector. Then since we presented these results first time in 23, so we also compared against C3 that was used in the SMT competition 2022. We compared against CVC5, also the SMT comp version, and the old Bitwuzla version that was still the fork of Boolector that we also submitted to SMT comp 2022. And we evaluated the new version of Bitwuzla on all the supported logics of SMTlib, which is to combine non-incremental and incremental, it's over 170,000 benchmarks. And we had a runtime limit of 1200 seconds and a memory limit of 8 gigabits of memory. And here we have the results on the non-incremental benchmarks. And the takeaway here is basically that the new version of Bitwuzla solves the largest number of benchmarks. So it also solves the most benchmarks in 13 out of the 23 non-incremental logics. And if you compare the solvers on the commonly solved instances, which means that the instances that every solver can solve, so that C3, CVC5, and the old Bitwuzla version can solve, we can see that we are slightly faster than the old version of Bitwuzla on these benchmarks. We are close to 3 times faster than CVC5 and more than 5 times faster than C3 on these benchmarks. And the new Bitwuzla version was submitted to the SMT competition 2023 the first time, and for the non-incremental track, we won 17 out of 30 gold medals in 6 divisions. And for the incremental benchmarks, you can see again here that the new version of Bitwuzla solves the largest number of queries, and overall it solves the most queries in 11 out of 15 logics. And again, the SMT comp, we won 5 out of 6 gold medals in 6 divisions.
Matthias, what is your feeling about how well these sorts of benchmarks align with real world use?
Well, we get every year we get new submissions to SMTlib, right, from different kinds of users. So it's either from academic research papers or from industry users. So we have a lot of different applications and different varieties of benchmarks in SMTlib. So that's also why we have so many benchmarks.
So the
So overall,
benchmarks are maybe they're not really synthetic the way that like the Chat GPT kind of benchmarks are. They're like real
no,
world things that people ran into
yeah.
that would be interesting.
There are some benchmark families in there that are for sure crafted,
Yeah,
right? But most of them are actually application benchmarks from
cool.
different kinds
Cool.
of applications.
That's super cool.
So, and we always encourage users if they use SMT solvers, right, and they don't really work that well on their problems, we encourage users to submit these problems to SMTlib actually, so that SMT solver developers have access to these benchmarks. And if they end up in SMT companies on it or in SMTlib, at some point developers will have a look at these benchmarks and try to improve their solvers on them. So it's always good to submit the benchmarks to SMTlib.
So I see, pardon me, I see that it is, however, noticeably slower than Boolector.
Well, in this case, so Boolector doesn't support all the logics that we support now. So Boolector doesn't have support for floating point theories and things like that.
Right. So it doesn't solve very many of them, but is that actually, that's a good question. Does the fact that it takes slightly over half as long mean that it takes slightly over half as long to solve 10% of the queries, or is that
it's for solving 60,000 queries, it takes 102 seconds. And Bitwuzla solves close to 700,000 queries and takes 172,000 seconds.
So it's actually a lot faster than Boolector.
Yeah, I mean, we could also do like commonly solved on the 60,000 or comparison, but it is a lot faster actually. Yeah.
That isn't clear from your slides. So the next version is talking about want to rearrange that.
Yeah. Well, I mean, we included Boolector here only for historical reasons because we say, well, Bitwuzla is the successor, right? But the thing is that Bitwuzla supports a lot more theories than Boolector does. So
Right.
we just included it it was the same also for non-incremental, right? So it's just a bunch of logics that Boolector supports. But we wanted to make the point that, well, when Bitwuzla supports a lot more, and we had to include the old version of Boolector to just have like a comparison. But yeah, we could have talked about more between Boolector and Bitwuzla, the direct comparison. That's a good point. Yeah.
Right. Well, one of the reasons is that one of the things that people are going to wonder about is should I switch from, if they were using Boolector, should I switch?
Yeah.
And that is, if they were using Boolector, it's because it handled what they were doing, and so that's about whether your switching is going to get you more performance. It looks like the answer is yes, at least on average.
Yeah. Well, that's the thing, right? So in the beginning of the talk, I also said that we will retire Boolector very soon, because now we have stable APIs in Bitwuzla, and I think we have all the features also that Boolector had or more features, and I think now we can finally sunset Boolector and just archive the repository.
Right, but given that it's apparently unmaintainable, you would probably do that anyway.
Yeah.
Even if it were slower. So it doesn't actually, that doesn't answer the question itself.
So, well, the thing is, I mean, once users start trying out the new version and they realize that there are some performance regressions, we hope that they will tell us, because we will focus on these and improve the new Bitwuzla on these problems. But we don't really know of these problems if the users don't try the new version. So
right. Well, I realize that too.
Yeah.
But one of the reasons I am here is that we used Boolector extensively in a past project, or I used Boolector extensively in a past project for a certain it's we, but it's not necessarily the we that Max is thinking of. And so I'm wondering was wondering if it is time to try switching that project, go back to that project, which is now like over, but go back to it, make it build again, try it with the new things, and see how much faster it is. And it sounds like it is time it sounds like it would be good to actually do that.
Definitely, yeah. Because right now, I mean, Boolector is already in maintenance mode for quite a while, and I mean, I'm also a part of the CVC5 development team, and now working on three SMT solvers at the same time is, yeah, it is too much. So Boolector is already in maintenance mode for a while, and we will definitely retire it. So at some point there won't be any support anymore for it. So I really hope that users will make the switch, and I hope that there are not too many performance regressions.
Right. Well, I will put that in my list of things to do, which unfortunately is, this long, but
yeah. But if you encounter any issues, let us know.
Yeah, will.
Awesome. All right, so yeah, it's also my last slide of the presentation. So, of course, obviously I talked about Bitwuzla, a new state-of-the-art SMT solver for all things bits. It's an open source SMT solver. It's licensed under MIT license, and you can find the source code on GitHub and website documentation also on GitHub pages. So yeah, thanks a lot for your attention.
Matthias, this is super cool. Thank you so much.
Of course, thank you.
I think one of the things that's always made me just really curious about SAT and SMT solvers is the kind of social aspect that, like, you have to solve problems that exist in the world, right? And those don't follow, like, if you were to make a type enumerator for, SAT equations, you would not generate the distribution that exists in the world of things that we are kind of interested in as humans. I wonder, did you encounter any like particularly nasty examples that really inspired you or were interesting to you when you were working on this, from users or from the real world?
Well, it's actually always, I mean, you always try to improve your tool. So if users have you recently had this, for example, with so there's OSIS that's a framework for hardware synthesis and stuff like that, and they're using the old version of Bitwuzla. And I told them, well, you should try the new version, and they did, and they had a performance regression. So, well, what do you do then, right? I mean, you start debugging it on the old version and see what the solver did, and then you have to run it on a new solver and try to figure out if something's missing or not, if any rewrites are missing, or if anything else is done in a different way. And that's always pretty much the story of our life as SMT solver developers. You always try to solve these problems faster, right? And I mean, the good thing is, at least if you have a solver that is already faster, then you can figure out what that solver does, right? But if you have new problems, well, it's very often involves a lot of staring at the benchmarks and try to figure out if you can do something smart to make it faster. But it's very often not obvious what to do. So you have to try a lot of things, and yeah. But it's not one specific set of benchmarks, but it's pretty much always the case that, yeah, you either are slower than a different solver on these benchmarks, and you want to figure out what's going on, or if users have performance regressions and stuff like that. Yeah.
Maybe you said this, but how do you compare to Z3?
On these benchmarks, for example, non-incremental, it's 5 times faster than C3.
Wow, that's nuts.
And that's the thing. So C3, I mean, is used a lot, right? And that's the thing. So first choice is usually for users to try C3 on their problems. But I mean, there is not one solver that is good in everything, right?
I've caused actually Stack Overflows in Z3 before.
Yeah,
which is an impressive level of screw up from such a theoretically battle tested software, right?
Oh well, I mean, it's still software. Bugs can happen.
Yeah,
and it's SMT solver is a complex code base, right? So I'm not sure about C3, but for example, CVC5 is around 350K lines of code, and then another 100K lines of code of generated code. So a lot of things can happen there, right? So Bitwuzla is, I think right now we're at around 55K C++ code. So it's a factor of almost 10 less, yeah. But that's the nice thing you get from a more specialized solver, right? So you can focus on a few theories. You don't have to be general enough to support everything in SMT, but you can really focus on this. For example, Bitwuzla on the bit vector stuff, right? So yeah, I mean, as you can see, I mean, bit vector logics, that's C3 is not really good on bit vectors. So it was that's already quite a while. And if you follow, for example, the annual SMT competitions, you see that C3 is usually on the very bottom of the list of solvers in bit vector logics. But yeah, it's still interesting to see that a lot of people just use C3 and never try anything else.
I suppose I have a question here about like, right, so Bitwuzla is designed for sort of bitwise or bit vector solving a particular subset of problems. I had a little bit of experience in the past with trying to add like some additional theory solver to Z3, and I guess I'm interested in like there on one hand there's trying to provide features to allow users to do this, and on the other hand there's like providing this functionality in such a way so it's easy for you as the developer to extend Bitwuzla if you wanted to add, I don't know, a theory for like some of the data types used for arithmetic in neural networks, right? Like those sort of more optimized types of.
Yeah.
But I guess my point is like, given you're working on Bitwuzla and also CPC5, like, do you have any thoughts on that? Like, whether it makes sense to provide the ability for users to do these things, whether it just requires too much understanding of all of the invariants that you as a developer, need to keep in mind when you're dealing with adding a new theory solver or something like that.
So yeah, I mean that's a good point because, for example, the C3 has an API for user propagators, right?
Yep.
So where basically users can implement their custom theory solvers outside of C3. But that's also really dangerous territory, right? Because you can make the solver unsound. So there is nothing you can safeguard within the solver to avoid that the user messes up on their side of the user plugin. So you really have to be careful about these kind of things. So we actually plan something to add user plugins in CVC5 so that users can actually have support for custom theories.
Cool.
That's on our, it's currently work in progress, but yeah, we're working on that. I don't think that we will have something for that in Bitwuzla because we really want to have to focus on bit vector logics, and that's pretty much it, right? So if you need, for example, real arithmetic and things like that, you should go to CVC5, C3, or other solvers that support these, like Yanks.
Okay, I guess the sort of it comes down to, for something like Bitwuzla, like you understand the users of this tool well enough to say basically this is all of this is a good base set of functionality here. These are going to work well in the problems that this community has, and like it's not super necessary to consider even for yourself as the developers of Bitwuzla, like how would you go about making it easier for you to add additional theory solvers in the future? Because as you say, like it's too challenging. Rather, it's very challenging to do this in a way that doesn't cause like problems logically that allows you to lose correctness. Or
I mean, the good thing is now with the new architecture of Bitwuzla, it is easy to add a new theory solver, right? But it's still, I think we will still have to focus on bit vectors and more hardware and software verification, not so much on other things like arithmetic and stuff like that, or string reasoning, because there are other solvers, and yeah.
Yeah, that makes a lot of sense. Thank you so much.
Yeah, of course.
I think there's room for somebody to write a really nice paper about if you're not an expert on SAT or SMT solving, but you think you need one of these tools, how do you choose which tool to use? And like go over a bunch of different types of use cases. Like you're building a binary analysis suite, you're building a model checker, whatever it is, right? And say kind of some decision tree for how you would decide which tool to use and what types of benchmarks and criteria you would look at. Because I find that like when I talk to security people, they think Z3 is the only SAT solver that exists, right? Like they don't even know that there are other ones. And I'm like, no, there's like 30 that outperform it every year, and they have no idea. So I think that'd be a very nice work if somebody wanted to write something like that.
And the thing is also, it's not really that straightforward, right? That you say, well, you know, if you have like bit vectors with uninterpreted functions, then always use this solver, right? Because it really depends on your application. It can happen that on your specific application, a different solver is better than Bitwuzla or whatever, right? I mean, you always have, as a user, you always have, I mean, probably the most important thing is you have to make users aware of there is a large set of tools that you could use, right? And you have to evaluate on yourself on your application what would be the best tool. I mean, of course, I also see, well, for a lot of users, it's just good enough to use C3, right? So they have a bunch of different things they want to have, and C3 provides it all, so it's the easiest. They use C3. I mean, there are also other reasons, like, for example, the Python bindings of C3 are really nice, right?
Yeah.
So it's really nice to use and really easy to use. So there are other things that users consider. I mean, with CVC5 and also Bitwuzla, we try to be as user-friendly as possible, and we are still working on it, specifically also for CVC5, to make users aware of all the features CVC5 has and how you can use it. And we also try to, I mean, we did a lot of work on the documentation of CVC5, for example, but there is still very often we get user requests or questions where, you know, I mean, CVC5 returns unknown and I have no idea what I have to do now, right? And then, well, then there is lots of different options you could try, and usually there is just one or two options you have to enable, and then it solves the problem. But I mean, users are not aware of it, right? So you have to start writing tutorials on what to do when things go wrong and things like that. So we're working on that. It's a process, but yeah, hopefully we will have a nice documentation. But overall, I think it would be nice to have like maybe an SMT lib level documentation, a tutorial that highlights all these SMT lib language features, but also where you can try different kinds of solvers, maybe in the browser and things like that. So it's, yeah, just to make people aware of all these different features and solvers and so on.
Yeah, that sounds great.
One thing, just to chime in here, that would be really interesting too, if someone were to write that as a paper or something, coming from the cryptography angle. One thing that we care about a lot is like approximate model counting. There's some like really interesting cryptographic things that is relevant for. And right, as like more of a security person looking at Z3, that is like not super obvious how you do that. So even just like comparing that feature would be fantastic for like my community.
Yeah. So there are groups, for example, there's a professor, I think he's now in Canada, Kuldeep Meal. He's working on approximate model counting. And he did work on this for subfolders, but also he's recently working on SMT approximate model counting. Not sure if you're aware of this.
I'm not familiar with his work, no.
Okay, but there are tools that are based on top of SMT solvers that actually do this model counting.
Oh, that's awesome. The only stuff I have seen required a grad student to like do on their own, and it was very janky. So I'm glad that there's better ways of doing it.
Well, it's still work in progress, of course. I'm not sure how far they got with on the SMT level, but I'll post a link at least for this that case. Let me find the chat here. So that's their approximate model counting they use for SAT.
Okay, so to go back to your comment about like documentation in the Python interface,
Yeah.
having like been a TA for a class that was using the Python interface for Z3, I think that, I mean, as you say, it is extremely nice. That is like, it's unlike, you know, you're not just basically calling like the C functions to say, okay, let's build up a assertion and add it, and sort of in a very operational way, but you just kind of just write your constraint very much like you might, you know, solve using write some equations using NumPy or SciPy and then solve them there in a way that doesn't, I mean, so that's something that I think
That's
it would be
really
great.
nice.
Yeah, it'd be great if there was something even like agnostic of the solver that provided that kind of functionality.
So the thing is, so when we worked on CVC5, the 1.0 release, we also implemented basically C3 Python bindings that is a drop-in replacement. So there is in CVC5 we have the base Python bindings that's more like a direct wrapper around the C++ API. And then we have this Pythonic API, which is basically the C3 drop-in replacement based on this base API we have. So we really try to make it easy for users to try also CVC5, for example, for their Python programs.
That's awesome. I didn't realize that CVC5 had that.
Yeah, I mean, so it's kind of funny because through a project proposal, we had to do interviews with our user base, CVC5 users, and we did 60 interviews within 4 weeks. And we heard it a lot, actually, so that users were not aware of these kind of features, right? So we have them in the documentation and everything, but it seems like we're still really bad with that advertising these features. So we have to work on that so that to make users aware of all these things you can also do with other solvers, with our solvers.
Another related topic is the question of when do you use bit vectors and when do you use linear arithmetic? And that is something for which, as far as I've ever seen anyway, there is not really any good guidance out there.
Yeah, that's a good one. I mean, it really depends. I mean, for hardware verification problems, it's kind of obvious, right?
Right, and the same is for software.
Same as for software, unless you have, for example, multi-precision integers and stuff like that. Then, so we have users, for example, that use integer reasoning with bit vectors, and they use the integer part for the multi-precision integers or infinite precision integers, and then they do like non-overflow arithmetic, right? And then they translate it back to bit vectors and things like that. So that will basically be, I don't know, in C++, if you use GMP to do some arithmetic on multi-precision arithmetic, and then you translate it back to bit vectors and do something with native data types. So it's tricky. So if you need bit precise semantics, then it's usually bit vectors are the way to go. If you don't necessarily need it, then it depends, I guess.
It does depend. Like just a couple of days ago, I was listening to a talk that someone else giving with that, listening to a talk someone else was giving, where they had decided to use linear integer arithmetic for all their machine integers, basically by applying bounds to all the operations. And they had decided this was a mistake, but hadn't replaced it because having built it fundamentally into all their stuff, changing it would have been a big deal.
Oh, wow, yeah, that's so then what you could try to do in this case is, right, so if you get like an SMT file and you basically encode this problem with integers, but as a bit vector problem, you could do like a translation from this problem to bit vectors. And then you could maybe at least try to
Right, maybe, but it's hard to do that. It's hard to do that and be sure that what you're doing is sound.
yeah.
The reason we end up using Boolector, this was like 4, 5, or 6 years ago now.
Mhm.
We end up using Boolector because we end up using bit vectors, because first we decided that because we're doing low-level stuff, we needed bitwise operators, which you don't get in linear integer arithmetic.
Yeah.
And then we discovered that combining integers and bit vectors in Z3 was really damn slow.
Mhm.
So we said, okay, everything's going to be bit vectors, and then we discovered Boolector, like, oh, great. And that was a considerable contributing factor of a thing actually working and being fast enough to be useful.
Awesome. So what kind of application was it that you were using Boolector in?
We were doing assembly language synthesis.
Uh-huh.
So we had these. So basically, what you do is symbolically execute a generic program, generate gigantic SMT formulas,
Mhm.
and then ask a solver to generate, like, it ends up being a set of control variables that tell you which program you're making.
Mhm.
And so you ask a solver for a model for the control variables, and then see if the program you got is good, which it isn't necessarily. But in assembly language, there's all kinds of bit stuff, and so it all had to be they're always definitely had to be bit vectors.
Mhm.
But as you won't be surprised to hear, Boolector was a lot faster than Z3 at it.
Yeah. Yeah, that's something we've seen in the SMT competitions for quite a while now. That C3 speed vector solver is not state of the art anymore. So for quite some while now. But it's still really good in other with other theories. So very often it's just good enough, right? But if you have these massive bit vector formulas that really where you have or need a lot of bit vector reasoning and a fast subsolver, if you do bit blasting, then C3 is not really a good choice. But the nice thing is, if your tool interfaces with the SMT solver via SMTlib, it's really easy to switch out the solver.
Right.
At least it should be very easy, unless you use solver specific extensions to SMTlib, which can happen a lot for C3, for example.
Or other glitches. I remember we had a lot of fun at one point with some solvers accidentally returning extra blank lines that would confuse the return parser.
Yeah, that's we also heard that a lot. So that's the thing, right? I mean, there is SMTlib. It's actually a language standard, so every solver should actually behave pretty much the same. But there are still very small differences, maybe in the output of the solver, how it prints S expressions. Maybe solvers print it and add extra new lines and stuff. Others don't, and it's You always so if you want to have like this generic interface, you usually still need like a solver specific parser for the output to read it in again, because solvers just output it differently, which is annoying, but yeah.
Matthias, we should probably end the hour because we've taken a solid hour of your time. But thank you so much for coming to talk to us today. It was a lot of fun.
Thanks for having me. It was
if
fun.
people have more nerdy questions, should they email you? What's the best way to get in touch?
Yes, please. Can you forward them my email address?
I can do
awesome.
That. Okay.
Awesome.
All right. Thank you, Matthias.
Thanks a lot, guys. Bye-bye.
Bye.